record. Okay, so before I start, any questions? We are currently in chapter 4. We are solving PDE with the finite difference technique. And particularly, we are looking at the standard derivative contracts.
So I have a question from chapter 2.
Chapter 2, okay.
Yes, page 64 of the book, where they calculate like Bermuda cosine method for Bermudan options.
Oh, cosine for Bermudan options. Okay, okay. So just let me open the book then. I didn't open the book. Okay, page 64.
Yes, sir. Can I just share the screen so that?
Sure. Right. So this is page 64.
Yes, just the last equation before page 64. Yeah, so they are calculating this. This is a like backward induction type thing.
This is backward induction.
Now, in page 64, for computing this, they are calculating these cosine coefficients for CK and GK. And finally, they are calculating like TM star. If you just go below. So these are our calculations. Now we are able to calculate the coefficients BKTM. First we find XM star. So why this XM star is coming? I'm not sure. Because why we are kind of solving this, like equating both these coefficients.
So this is essentially the boundary. XM star is the boundary. Because when you are doing backward induction, you look at where exactly the two choices are going to give you the same payoff. One in expected term, the other in actual terms. So any problem, you essentially partition into two sets of values. One set where you will continue and the other where you will exercise immediately. And the boundary here is XM star.
Okay, sir.
So if you are thinking of a call option, then XM star is the lowest point where you will exercise the call immediately. Below that, you will continue.
Yeah. Okay.
We will use this idea again. So we will use this idea again. So there will be other occasions where the same backward induction and this marginal indifference will come in. That's why I essentially gave you that informal introduction to backward induction, because that principle is, apart from its general nature that it is applicable in many sciences, that principle is very useful in finance. But we don't have any formal topic like that. So maybe in future I will add that to the course. I think that makes sense.
Okay, sir.
Any other questions?
No.
Okay. Anyone else? All right. So then I assume that you are more or less clear on things. So let me then continue with chapter 4. So in chapter 4, our primary objective is to use the technique learned in chapter 3 for derivative pricing. And we have already seen the use of the explicit discretization last week. We have seen the use of the explicit discretization scheme for solving our standard Black-Scholes PD. So obviously we know there are other techniques with different stability and different rate of convergence. So we will discuss implicit and Crank-Nicolson also. So let's begin today with Crank-Nicolson, and I think I will need to. No, you can see my screen already, correct? I am sharing.
Yes, sir. We can
Yeah,
see.
yeah. I got confused. Okay, okay. You are actually seeing my screen. No problem. So implicit discretization is now going to be used to approximate our generalized Black-Scholes PD. Very similar to the explicit technique. So we will basically go through this quite quickly. We have already learned what is implicit discretization, and that is in section 3.2.2, last chapter. So what we do is we consider the grid point xj and tau k plus 1. Because in implicit, what we do is we do backward approximation on the timeline. So for the theta term, del v hat del tau, we are going to go backward. So I start from one step to the right. Again, I use the central difference for the second derivative and the first order central difference for the first derivative with respect to stock price. So if we use our backward approximation for theta, then my del v hat del tau will be given by this expression here. Going one step back, the gamma term, second derivative, will be given by this central difference. So I am at xj tau k plus 1. So I am using j minus 1 k plus 1 and j plus 1 k plus 1 on the two sides to get my central difference. And the delta term, using a similar approach, two steps, we will use j plus 1 and j minus 1. And the associated errors are of the order of delta tau and delta s square. So again, we set up the difference equation, ignoring the error terms. So at xj tau k plus 1, our difference equation will look like this object here. And then we do the usual stuff. We multiply by delta tau and rewrite this difference equation as 416. So where 416, where we have this term like rho that we used earlier. So this delta tau and delta s square ratio is appearing again, and there is a delta tau delta s. Now, remember that we redefined certain symbols to make the notation easy. So in 4.6 and 4.7, we defined alpha and beta to replace these two ratios. And these ratios appear again in the implicit difference. So we will use it again. Using those symbols, what I have is this equation here. I think I will make it slightly bigger. So using the alpha and beta symbols, the equation 416 becomes like this, where the subscripts are adjusted because we are now doing backward difference. And again, we define new variables LD and U as before, using this kind of constants. So this LD and U now replace our coefficients here, which are longer to write. So I get a more compact version of the difference equation in 417. So 417 is the form which we are going to finally look at. So is this clear so far? So it is just a standard implicit discretization scheme for Black-Scholes PDE. These were the original terms, which then we put together and use the symbols alpha, beta, L, D, and U, etc., as in the explicit scheme, to finally arrive at an equation which look like 417. So it's actually a system of equation, of course, system of equation 417. So where these L, D, and U coefficients appear in the equation. So Vjk is written in terms of k plus 1 terms. For the sake of clarity, we also want to mention that we can relate these LDU coefficients in the explicit scheme in 410, 411, and 412. So if we keep these three in mind, we have the new L hat, D hat, and U hat coefficients for the implicit discretization, and these are related. You can check that L hat is just minus L, D hat is 2 minus D, and U hat is minus C. So I'm just relating 4, 10, 11, 12 with this system, this new system for the implicit one. They look very similar, and of course they are related. Why do we need this? Because when we use them together in a scheme like the Crank-Nicolson, then we don't want to be working with two different sets of variables. So we want to relate them to each other so that we can translate one to the other. So now our implicit scheme, which is 417, this system of equation, can be written in a compact manner like this matrix equation. So A implicit times Vk plus 1. So this is the left hand side of the equation. A implicit is the matrix of these coefficients. The coefficients I am stacking in A implicit k plus 1. These coefficients L, D, U, L hat, D hat, U hat. In terms of that matrix, the equation 417 becomes A implicit Vk plus 1 equal to Vk plus the boundary correction. This we have done before, and we know that it has a lot of order confusion. So you have to be careful whether the order is correctly specified here also. So can you just check? Because the same problem happened in the explicit discretization also, that there was some order confusion. So are you checking? Anyone?
Yes, sir, it is okay.
Okay.
Yes, it's okay.
Good. So this is our implicit scheme in matrix notation, where A implicit is this matrix. And now that we have explicitly related the two sets of LDU coefficients, we know how to relate A implicit with A explicit, because we will need that later. In Crank-Nicolson discretization, we are going to use both of them. So before moving on to it, I have the explicit solution in 414 and 415, where the symbols LDU are defined like this above. For the implicit scheme, I have the equation system here as in 418. Again, with this L hat, D hat, U hat defined as above. So we know that we can also combine these two to get a better approximation as in the Crank-Nicolson scheme. So this is section 3.2.3 that we are referring to in the last chapter. So the Crank-Nicolson is based on averaging of forward and backward finite difference approximations. So what we will do is we will just add up 413 and 417. So 417 is the implicit scheme, and of course 413 is the explicit scheme here. So we are going to combine these two. So in effect, we will be combining these two matrix equations. Anyway, so the first, the equation in scalar form look like this. So I'm averaging 413 and 417. If I do that, then this is the form of the equation. For 17 and
So there is an equality missing.
there is an equality missing. I typed it.
So it should be real, like immediately after the first equation, right?
Yes,
Like the,
yes.
the topic.
Just a second. Actually, there were mistakes in the book, so I retyped it. And where did I make the mistake? I made the mistake here. Thank you. I just noticed it as I was talking about it. So basically, the k elements are related to the k plus 1 elements through the Crank-Nicolson scheme. So that's the relationship. So the first line is actually the left hand side, and the second line is the right hand side. And how do I get them? I basically add up explicit and implicit. So I have both kinds of terms appearing here. Now is this okay? Can you just quickly check that if I add up these two sets, 13, 17, 13 is here, then this is what I will get. This is written in terms of alpha beta, not LDU. So I think it would be easier. It would be easier to look at 4.9. 4.9 here. Yes. Easier to look at 4.9 and this equation 416. This one. Because these are in terms of alpha and beta. Because 417, 413 are already in terms of LD and U. So that would complicate matters. Okay. So the two original equations in terms of the alpha beta coefficients, they are added up. So I will not write these numbers here. I should correct it. So I'm looking at 49 and effectively 416. Okay. So is this okay now? The explicit and implicit schemes are added to arrive at the Crank-Nicolson scheme. I'm not using the LDU symbols, so I just made this correction here to make the connection explicit. Now, this is in terms of the LDU notation. So here I had the original alpha beta notation, but now we can change it in 419 to the LDU notation, where the left hand side I have the L hat, D hat, and U hat symbols as in the implicit scheme. And on the right hand side, I have the explicit scheme symbols. But of course, they are related to each other, so I don't have a problem. And this is the relationship here, restated. Okay, so can you just check and tell me if this looks consistent? Because in the book, there were some typos. If you are looking at the book, which you should, there are some typos involved. So this is the Crank-Nicolson scheme discussion here. And this is the equation system that is written. But there are actually problems with this. So what I did is simply check and redo the equations. And if I am correct, then this is the right equation system. And then using that, we will go back to the LDU notation to get 490. So please check and confirm that this is indeed correct. Has anyone checked?
Yes, sir, it is coming.
I mean, okay, good, good, because with HITSA, I am never sure. And I also make a lot of mistakes. So I thought it would be a good idea to get it checked. So this is what we have in terms of the LDU, so that now I can write the Crank-Nicolson matrix equation in this way here. So now the system is looking slightly more complicated, of course, but it is, if you recall the original explicit and implicit scheme, it is the same as those, that I now have A implicit plus I VK plus 1 written in terms of A explicit plus I VK plus the correction term. So what we will do is we will invert this I plus A implicit and solve for VK plus 1 in terms of VK. And if you remember that again, implicit plus I will be a tridiagonal matrix and order of n computation. So we are good. So
Can you go back a bit?
yes, of course. How far back?
There, the Crank-Nichols
Crank-Nichols.
I was just checking.
Yes.
Yes. It's all right. Yes.
Yeah. So this is the one I wanted you to check, because I found, actually I did not find last year when we were doing this course, students in the previous batch, they identified problems, so we worked it out. So I just wanted to do a double check whether it was indeed right, because right after that the pandemic happened and most of these things flew out of our head. So I'm now getting back to them and just making sure that we have done the right thing. So this is the Crank-Nicholson scheme. Now it is quite familiar to us. So again, we are not going to discuss the multi-step, because in multi-step it will be much more complicated than this one. It will not be a simple linear system like this thing, because there is a second order adjustment involved in multi-step. But for Black-Scholes PDE, the Crank-Nicholson or the implicit scheme are quite good, as we know that they are unconditionally stable and their approximation order is reasonable. So in practice also, these schemes are quite popular, even now, quite popular. So any questions at this point? So we have looked at the Black-Scholes PDE. So let me now go back to the origin of the problem, because we are now going to discuss a few other issues. So we started out with the generalized Black-Scholes PDE, and we have now learned the finite difference approximation in 3 approaches for this system. But initially, we did not talk at all about the boundary conditions. So I said that for the time being, let us assume that the boundary conditions are fully known, and then try to solve the system. So here I said that we assume boundary values are known, and I said that we will discuss later. So now let us come back to the boundary condition discussion. Now that we know how to do the approximation given the boundary conditions, now let us talk a little bit about the boundary conditions, because boundary conditions are going to be critical. How we are going to manage our ceiling and the floor are very important in any finite approximation. So the choice of boundary conditions can be critical for ensuring the accuracy. Of course, we know that. So what do? We are fitting a mesh. We are basically placing a grid or a mesh, and we want to place it strategically. Strategically in what sense? That there are certain values which are more important to us. Certain values in the sense stock prices which are more likely to be realized. So the way we want to place our grid, place our mesh, so that these critical points are either exactly matched with one of the lines, one of the horizontal lines, or it is very close to an exact line. Because we are restricted to steps of delta S, not all points can be covered. So we want to make sure that the points which are more important to us are either exactly covered on the grid or they are very close to the grid. An easy example is, and that usually improves the accuracy of the algorithm, because if more likely events are approximated better, then overall my approximation error will be less. A standard example is, I want to match the strike of an option. So if the strike is exactly matched, then of course I have a better approximation. And the strike is known deterministically at the start of the contract. We also want to match the timing and amount of the dividend payments. Typically, dividend payments are uniform in nature. They are prefixed in calendar time, like every quarter or once every 6 months. Whatever it is, usually we know what are the dates when dividends will be paid. So we also look at the horizontal axis, the time axis, and select our grid in such a way that the dividend payout points are on the grid. Similarly, if we can, we also want to match the amount of the dividend payments on the vertical grid in terms of delta S. Because again, dividend payment amounts are typically, they can be anticipated, like 1% or 2%, like that. Other important considerations could be matching the barriers. If we are considering a barrier option, then of course I want to match the barrier with my pay. Similar to the dividend payment timing consideration, timing on the horizontal axis, if we are considering a Bermudan option, so we have been discussing the barrier option and the Bermudan option quite a bit as path-dependent examples of path-dependent options. So for Bermudan options, we have a discrete set of exercise times. So again, if possible, we want to match that set with the grid. So if those exercise times are uniformly spaced, then it would be possible for us to do so. Okay, so am I making sense here? So right now, what we are trying to do is trying to strategize how to handle the boundary conditions. And in addition to that, we are also trying to find out what are the more important points where our grid should be placed. What are the more important values or more important time points, so that we can adjust our grid, we can translate our grid in such a way that those important points are exactly on the grid as far as possible. If they're exactly on the grid, that would be very good. Then we have the best approximation because we are going to calculate the value at that point exactly and use it in the algorithm. If not exactly on the grid, we would at least want to keep it very close to the grid so that whatever error of approximation we are making, it would be small. So is this clear? What we are trying to do?
Sir, could you repeat it once more?
Okay. So our question now is about the boundary conditions, which we initially assumed to be perfectly known, and the grid was decided, and then we did the discretization schemes for the approximation exercise. Now we are coming to the boundary condition question. So far, all we know is if we are using a grid, then we are evaluating the function values exactly on the grid, and we are approximating that function value in between. So it's like a lattice. So it's a grid points are discretely spaced. So when I am on the grid point, I am calculating the function value exactly. But if I am between two grid points, either on the timeline or on the value line, I am approximating. It could be first order, second order, but it is an approximation anyway. So now the question is, what are the points where I want my approximation to be better? Ideally, I want an exact value. There could be certain time points in the lifetime of the contract where I want more specific information. What could be the examples? The examples could be for a Bermudan option, I can think of all the possible exercise times, the set of exercise times, and I want all those time points to be on my grid so that my calculations are exact, at least on those points. Another common consideration is I want to match the dividend payment timing with the grid. If I have a long-lived option and there are dividends that are going to be announced on the stock, the underlying stock, during the lifetime of the option, then I also want to match the dividend timings with the grid. Or in other words, I want to move my grid so that the dividend timings are exactly covered. Is this clear so far?
Yes, sir.
Now, similarly, think of the vertical axis, the value axis. there also some points are more important than the other points. For instance, I would like to match the grid with the strike price. Not only that, I have a fairly good idea what range of the stock prices are more likely. And in that more likely range, I want my approximation to be better also. Because then on an average, my approximation will be good. So typical examples are, if I am looking at a barrier option, then I want to match the barriers, whether it's above or below. I want to match the barrier on the grid, so that on those important points, which HITSA calls critical points, my error of approximation is either 0 or small. Is it okay now?
Yes, sir.
So now what we will discuss is essentially how to achieve this. So these are strategic things. Strategic in the sense that I am going to select my grid in such a way so that I achieve my goal. So we will start a discussion of implementing boundary conditions, where the first strategy is the Dirichlet boundary condition strategy. Okay. So what is the premise? So the option value at tau equal to 0 is our initial condition, which is actually the time of expiry. This is perfectly known because that will be just the payoff of the option. So I know that Vs0 will be Fs, where Fs is the payoff of the derivative at expiry. Remember, we have reversed our timeline. So tau equal to 0 is the expiry date. So initial condition is much easier to figure out. So what we are more concerned with is the floor and the ceiling, the boundary conditions on the value axis. So for that, remember again that we needed to fix a minimum and a maximum stock price beyond which we will not do our calculations, because after all, we need a finite grid. So we need to fix an upper bound and a lower. So the boundary conditions are sometimes not that difficult to figure out. For instance, if I take the minimum stock price to be a very low stock price, then I can simply say that for a simple vanilla call option, the value of the contract at that very low stock price at any point of time will be 0. Because if the stock price is so low, then nobody is going to use the call option. Correct? Is it clear?
Yes, sir.
But we are not always this lucky. Sometimes option contracts are complicated, so it is not that easy to figure out those conditions. But we have some general strategies which usually helps us. So the first strategy is the Dirichlet boundary condition strategy. So Dirichlet boundary conditions, what happens here is we specify the derivative value explicitly at the boundary points. So instead of trying to specify the function value, we specify the derivative value. So a call option at, say, the minimum stock price, we set the derivative value to be 0. For a put option, exactly same logic. At the highest stock price, S max, we can also set the derivative price value to be 0. So these are, in some cases, as I said, easy to decide. But we need to do something more. So we can also approximate a Dirichlet boundary condition for the value of the call at minimum or a put at maximum by simply setting the option value to be its payoff at that level. So we can say that, okay, let us calculate the payoff at that level. And in a normal volatility regime with a reasonable sigma, even if we calculate that explicitly, we will still get a value very, very close to 0. Even considering an unbounded support for the normal distribution, because the tail probabilities go to 0 very, very fast, the exact calculation would still be practically 0. So there will be no error involved. But if I am in a high volatility regime, sometimes exceptions may occur. Sometimes what will happen is, in a high volatility regime, the value of a call at a high level of the underlier may exceed its payoff. That is because sometimes people anticipate harder times ahead. When there is a high volatility regime, the perception starts playing a role. You not only look at the expected value, but you also try to anticipate the future. So in a normal situation, in a normal volatility situation, the Dirichlet type boundary conditions would be very reasonable, even if we use the exact expectation operation, unless we are in a very volatile time when the stock price is behaving very erratically, huge fluctuations, and then this anticipatory expectations may create a difference with the expected value. So this is one set of boundary condition, Dirichlet, and they normally work very well. It is very simple to specify, and it will work well unless we are in a very high volatility regime. So this is one strategy, which makes very good sense. Another possible strategy is the Neumann boundary conditions. So Neumann boundary conditions talks about the function itself. So we look at the partial derivatives. So we know that we are involving del 2v del s square, del v del s, and del v del tau. So we don't look at the derivative contract, we look at the function, and then we specify the partial derivatives at the boundary. So it is like an indirect way of specifying the value. So we don't specify the value of the derivative contract itself, but look at its rate of change quantities. So Neumann boundary conditions can be used at both the minimum and the maximum. This is sometimes useful. This can be advantageous, as the second derivative of the option payoff is often well known at extreme asset values. Typically, what happens is this kind of derivatives gets flatter and flatter as you go far out to the left or far out to the right. So a typical Neumann boundary condition would be specifying the second derivatives at the minimum and the maximum stock price to be 0. So for each time point, I am directly specifying the value of the partial derivative rather than the actual derivative contract. So I am using derivative in two senses here, so just be careful. Of course, you have to remember that when we are using central difference, we are going to need two initial values, two sets of initial values to make our approximation. So if I want to approximate the first vertical right after the boundary, no, the first horizontal, sorry, because we are talking about floor and ceiling, the first horizontal, and I try to do a central approximation, then I will be thrown outside the grid. You remember that you go 2 steps back, so you'll be outside the grid. So typically what happens is, near the boundary, people are forced to use only a single difference. So we can use the forward difference for the left boundary, for example. So at S minimum, when I am approximating the second derivative, what I am going to do is, I am going to set it equal to the second derivative at the first horizontal after the minimum, so just above, and then I make this approximation. So For the first ones, we do not get second degree approximation, second order approximation. So you will just get a first order approximation. Is this clear? So now I am talking about the partial derivatives which constitute the Black-Scholes PD rather than the actual derivative contract. So our approach is now specifying those derivatives directly, and the challenges for the central difference would be I have to make a further simplification for the horizontals just above the minimum or just below the maximum. Is that clear?
Yes, sir.
Yeah. So a typical justification for that could be that we can argue that if the second derivative is 0 at a boundary, then I can also assume it to be 0 at the adjacent point. It's not a very good logic, but it's an empirically reasonable logic. That instead of assuming it to be 0 at only on the boundary, you also come a little bit inside and still assume 0. So that's what we have been doing here. So basically what it says is that we are not only assuming the second derivative at S mean to be 0, we are also assuming that the second derivative at S mean plus delta S to be 0 and S max minus delta S to be 0. So if I make those two sets of approximations, which usually make reasonable empirical sense, then it allows us to use the central difference because I have two zeros and I have the tridiagonal structure in our stiffness matrix. So stiffness matrix are those A matrices that we talked about. Okay, so I will take a break here because first of all, it's about time, and also you should think about the boundary conditions a little bit because we are going to talk more about them in slightly more complicated settings in the second period. So are there any quick questions? Otherwise, we will resume recording. Share screen. All right. So we talked about some of the boundary condition strategies, in particular Dirichlet and Neumann boundary conditions, which are Dirichlet is on the derivative value and the Neumann boundary condition is on the partial derivatives itself. Now, there is one particular situation, which is this announcement of dividends, which is a very simple candidate for a jump in the stock price. And this is particularly important because a jump, as we already know, because it's a very sudden change, is much harder to accommodate in any smooth model, any differential model. So we have already discussed this thing in the boundary condition discussion here in general, that we want to match the dividend payment timings. Why is it particularly critical? Because right after the dividend payment, the stock price gets suddenly reduced. Because if you remember last term, what happens is dividend is paid out of the value of the stock. So the value of the stock is reduced because dividend is paid out, which means the share prices are also going to jump down. This is not the only jump situation, of course. There could be other situations where there might be a jump in the stock price, the underlying price, but dividend is one particularly common situation where we see a jump, and thankfully most often it's a deterministic jump because both the timing as well as the rate of dividend are known from beforehand. So this is something that we definitely want to handle using our grid adjustment. All right, so what happens is when we have suppose only one known discrete dividend payment time. So suppose I know that there will be a discrete dividend payment capital D at time TD. So that means after the change of the timeline, the value at tau D plus and the value at tau D minus will have to be adjusted because the underlying stock price are now different. You have to remember that tau D plus is a time point just before dividend and tau D minus is a time point just after the dividend. So just after the dividend, the stock price has become S minus D. Okay. Is it clear?
Yes, sir.
So again, we want to adjust our grid so that tau D is one of the grid points. Tau D is on the grid, on the mesh. So we adjust the time step to coincide with tau D. So suppose tau D on the grid is tau K. So it is the kth time step tau K. So what are we going to do when we are doing our finite approximation? After the completion of the solution at time tau K, or to be precise, tau K minus. So we are going backwards, remember. So tau K minus, we have the value up to and just before tau K, which we call VIK minus for all I. So for all I, which is the value axis, I have the value. Now when I want to proceed to the time point tau K plus 1, which happens to be before the dividend, which means the stock price is different, the option value at SI should be replaced by the option value at SI minus D. So this is the equation that is going to be used for the calculation of tau K plus 1. So does it make sense? So as long as I did not reach tau K, coming backwards, remember tau is reversed, there is no dividend adjustment. But as soon as I cross tau K, that becomes in a pre-dividend time, which means the stock price itself will be different. So I need to make a replacement in the stock price argument. Is it clear to you?
Can you repeat the argument?
So we said that during the lifetime, there is only one dividend. So the only adjustment to be made is at TD. This is without loss of generality, because if we can handle one, then we can handle any finite number. That is not a big deal. To understand the concept, let us assume there is only one dividend at TD, and I have adjusted my grid so that on the grid, tau K, time step tau K is equal to tau D. So what is happening at tau K? When I am doing my computations, as long as I am before tau K, there is no adjustment required. So up to just before tau K, I can calculate the values for all I, no problem, because there is no change in the underlying. As soon as I cross tau K, when I am going to calculate my values for tau K plus 1, the next point on the grid, then the adjustment has kicked in, because now I am in the pre-dividend time. And in the pre-dividend time, the stock price will have to be adjusted by D. So the option values will also be changed, because this equation here will translate into the discrete approximation. Okay, is it clear now? So
Okay, sir.
remember, we are going backwards. So when I am at small tau k values, that means I am close to the expiry. So it is after the dividend. So no adjustment will be required initially. Just when I cross the dividend point, that's when the adjustment will happen. And it is going to happen only once because there is only one dividend. All right. Are you all clear about this?
Yes, sir.
Now that brings us to the next question that, okay, we were talking about tau d minus, tau d plus, which are like infinitesimals, so very small. But I am restricted to a discrete grid when I am doing finite approximation. So in some sense, my tau k plus 1 should be close to tau k. In other words, it might be helpful if I could have a spacing which is not uniform, because I will want better approximation near the dividend point, the dividend time. So my tau k plus 1 and tau k difference should be ideally smaller than this difference at the other time points. But so far, we have only talked about a uniform grid spacing. So we have talked about a single delta tau and the single delta s. So there is no question of having closer and further away in the grid. But sometimes, as in this situation, a non-uniform grid spacing is useful for us. So that's what we are going to discuss now. So we can actually handle non-uniform grid points in two ways. One is just directly lay out the grid point as you want. So in the middle, you will have grid points closer to each other. And when you are closer to S minimum and S maximum, you can make it further off. In terms of timeline, if you have those important time points like dividend, you will make the grid finer near that point. And in the other places, you can make it further away so that the total number of points remain the same, but there is a concentration around the critical points, what HITSA calls critical points. So I can directly lay out a grid which is non-uniform. But then the algebra will become messy because for each step, I have to remember what is the relevant grid length. The other way, which is more elegant, is using a coordinate transformation. So if you recall the standard transformations, like a sine curve or a tangent curve, those transformations typically make the grids non-uniform. So if I have uniformly spaced points on the x-axis, I transform them using a trigonometric curve like that, the points on the y-axis will become non-uniform. So that's a more elegant way of achieving non-uniform grid points. So these are the two strategies that we will discuss now. One is the direct unequal subintervals, non-uniform grid, and the other one is the coordinate transformation. Okay. So consider the grid points like x0 to x capital N. So now we are going back to chapter 3. We are talking about the general notation starting from the Taylor series approximation, but Taylor series with non-uniform spacing. So suppose without loss of generality, I just have two regimes. I have one switching point in the grid at xi. What does that mean? That means all the spacings up to xi are uniform with distance h1, and all the spacings after xi are again uniform with spacing h2. So I am just using two spacing rules. The change point is at xi. So the points before xi are h1 apart, the points after xi are h2 apart. So if I am working away from xi, if I am near x0 or near xn, then I am essentially facing an uniform grid, so there is no problem in my approximation. The usual approximation formula will still work. The problem will be at the point xi or just to the right or left. So the interesting quantity here is to approximate the two derivatives f1 and f2 at xi. If we handle that well, then the rest of it can be easily handled. Now let's look at the two difference equations here. These are the two relevant equations, backward and forward. And now the differences are apparent because when I go backward, I can go backward by h1. But when I go forward, I will have to go forward by h2. So these two are the two different species. So if xi minus h1, the formula will be with h1, and forward it will be with h2. So when h1 equal to h2, we know what to do. We can directly subtract and get a central difference. All nice. Obviously, now we have to do a little bit more. So what we do is we do the usual variable elimination strategies. So for the first derivative, we will multiply the left equation, the backward equation, by minus h2 square and the forward equation by plus h1 square. And then we add them because I want to eliminate the middle term. So if I now add them, the middle term gets eliminated. So now my equation involves the function value, the first derivative, and the third derivatives, which obviously is our candidate for the error. So therefore, if I solve for f1, I will get this expression as in 422, which is obviously more complicated than the usual ones. But if you look at this expression and use a little bit of approximation, we do a lot of approximation in numerical analysis, so this is fine. Then the first derivative can be approximated by this constant times xi minus h1 value, this weightage into fxi, and this weightage into the forward value. So it is still like a central difference, only this 1 to 1 in the symmetric situation, the coefficients were 1 to 1. Now the coefficients are weighted by h1, h2. And the order of approximation can be figured out from this residual term that we ignore, which will be of the order of h1 into h2. Okay. Is this all right? Probably some of you have seen this before. I don't know what happened in your numerical analysis courses earlier. But just for the sake of completeness, this is the explicit derivation for the first derivative. Is this already known to you, or is this something that have not been covered? I don't know, because when we were students, this kind of things were not covered. We only worked with uniform spacing. And of course, the coordinate transformation, that was fine.
Sir, this was not covered earlier.
But is this clear now? Because this is just simple algebra. This is like, I don't know, class 8.
Yes, sir, this is clear. This is clear.
Yeah. So this is our approximation for the first derivative with the order of approximation. Similarly, one can also look at the second derivative, because remember in Black-Scholes we need the first two derivatives. So for the second derivative, again we look at 420 and 421, and now of course I need to keep the second derivative because this is where the action is. I want an approximation for f2. So now what I will do is we will multiply these two equations by H2 and H1. So earlier we multiplied by minus H2 square and plus H1 square because we wanted to eliminate this F2 term. Now our objective is to eliminate the F1 terms. So accordingly, we multiply by H2 and H1. So multiply by H2 and H1, adding up, the first derivative will vanish and we will have this expression, backward and forward function values equal to, again, the middle function value with some weightage, the second derivative, and again, the third derivative term, which would be our order of error. Now, then F2x, if I solve this equation, so I'll be dividing everything by this whole quantity here. So F2x will now be given by this more complicated weighted average, of the function values. So I will have this h2 times xi minus h function value, h1 plus h2 times fx function value, and h1 times fxi plus h function value. So again, the uniform weightage goes away. So 1 to 1 goes away, replaced by h2 and h1 weightage. The denominator is this. So in effect, my error term here in 423 now becomes order of h1 plus h2. So obviously the first term is my approximation. The second term is my error, which is of the order of h1 plus h2. So this is one way of doing the non-uniform grid point calculations. So now we know how to do it for one change, but then any finite number of changes is fine because any practical strategy would be having a finer grid in the middle and a coarser grid on the outside. So there will be two change points. So basically we will have a larger step size on the left and right extremes and a smaller step size in the middle. So there will be two change points. So in two places, the derivatives will have to be approximated using this weighted formula. Otherwise, it will go on as before. That would be a very simple way of implementing non-uniform grid points. And writing a code would be fairly easy. Okay.
Yes, sir.
So now let me look at the other problem, which is more algebraically elegant actually. So the other approach is coordinate transformation. So now basically we explicitly target that I want to have finer grid points near the critical prices, could be the strike, could be the barriers, etc. And in all other places, I can have a coarser grid. So the setting is the following. So suppose we are interested in finding this transformation that maps an interval 0 to 1 to this interval S minimum to S maximum. So basically xi will be mapped to the stock price, but in a particular way. What is the way? The way is that the uniformity will be on the xi line, on the xi space, but it will not remain uniform on the S line. So the function will be such that uniform spacing on the xi line, 0 to 1 line, will get translated into non-uniform spacing on the S line. That's what we wanted, right? So basically we'll do back calculation. So suppose what we want is a concentration around some point capital B in that domain. So there is a particular critical point B in the domain where I want a concentration. So what I will do is I can make a transformation from xi to s. An example is this sin h transformation. So are you familiar with sin h, cos h, etc.?
Yes, yes, sir.
Yes, sir.
So they are basically exponential functions, so not tricky. And we know that exponential functions have very nice properties. So this is a nice and easy transformation from 0 to 1 uniform spacing to stock price axis non-uniform spacing. In particular, the non-uniformity will be a concentration around this point B. So near B, there will be more grid points, and further off, there will be lesser density of grid points. So the grid points will be further and further off. So S xi equal to B plus alpha sin h C1 xi C2 1 minus xi is a candidate like that. There could be many other candidates, but this is an easy example, and to understand the concept, this is good enough. Now there is some work for you. So I'll go to the book page. So in this particular section that we are talking about now, which is coordinate transformation, so the details are actually here, the coordinate transformation and where B will be coming from, etc., and how these C1, C2 constants are to be solved. That I know you can figure out very easily, so I don't need to discuss. The homework is the following. The homework is, I want to use this transformation, coordinate transformation, to solve the Black-Scholes PD. So again, I have a particular stock price around which I want the grid to be finer, and it can be coarser far away. So basically my stock price will have to be mapped. And again, this is the candidate that is used in the example as we have discussed. So my PDE will also be transformed. All the partial derivatives will have to be evaluated in terms of xi, and you will get a final set of equation with the initial and boundary conditions in place of the Black-Scholes PD. So the homework is to study that coordinate transformation. It is not very complicated, but a little bit of algebraic detail. But if you go through that example, then the coordinate transformation and its usefulness will be clear. As I said, the transformation and the related calculations are very elementary, but the importance is in the convenience that you get out of it. So that is what I will leave for you as a homework. And I want to move on to other things that I want to discuss. All right, so far?
Yes, sir.
Okay, so there is one more important issue to be mentioned before we go on to further computations, and which is dimension reduction. What is this dimension reduction problem? The issue is when we are using methods like binomial tree, as in the Cox-Ross-Rubinstein model that we learned last time. The binomial trees, if we don't make them very simple, like recombining and everything, the computational load grows very fast. Because at every point there is a branching into 2 points, and we have a 2 to the power n kind of tree if we don't use recombination. If you think about it a little bit, and it is proved by Rubinstein formally, that this branching process where we are doing all our calculations, they can in fact be related to a finite difference scheme. Because at each step, we are essentially combining the two branches in the next time point. We go backward in time, remember? It works actually like an explicit finite difference scheme. So you can map it to a finite difference scheme. So you know whatever convergence and stability properties a finite difference scheme has, that will be inherited by the binomial tree method. It is not that easy to prove. You have to need work because this is actually a formal proof. But intuitively, at least, it is not very hard to understand why this should be so. Because at each time point, I'm essentially averaging the 2 points immediately to the right, immediately at the next time point. My scheme can be mapped into a finite difference. And of course, it's finite because I'm using a finite grid. Only in place of a rectangular grid, I am using a tree. But the logic is similar. Now, if I were to use a binomial tree for our auction price calculations, we will typically not want to solve for all the grid points, because some of these grid points are so far out, they might become irrelevant. So at each time point, we try to judge which are the relevant points, which part of the tree I need to evaluate. And hence, I can reduce my computational burden quite a lot. That's how we typically come to a realistic computation time. Because if we were to solve for the whole tree all the time, that would be too much work to do. So typical tree methods do not solve for uninteresting parts. The same logic, in some sense, have been tried in the rectangular grid system. So when we are using explicit method, explicit difference techniques, can we reduce the number of points where we want to do our computation? So how does it work? It works in the following way, that if at any point of time I am at a particular asset value and the time remaining is not much, so I'm close to expiry, then the relevant values of the stock price now would be much less than the original range from S minimum to S maximum. Think of the tree. Now superimpose that tree on the rectangular grid, and then what I am talking about will be clear. As in a tree, if I am already at a lower branch, I will start ignoring the very high branches, or vice versa. Similarly, even if I am working on a rectangular grid, if I am low on the vertical axis, on the value axis, I can start ignoring the very high points on the vertical axis. So this is another computational strategy that is often implemented in such finite difference algorithms. That if you are doing the computation in real time, because you see, real time is the key issue. We want to make the computation faster and faster so that it can be implemented in real time. Now, in real time, the advantage is you can update your knowledge. You know exactly what the stock price is currently. So what you keep doing is solving for a smaller neighborhood at any point of time. So in effect, I am only looking at a subset of the whole grid, and the computational burden will be reduced. Is this clear? Am I making sense? Some of these issues may not become so clear before an actual problem solving, because some of these things you learn only by doing them. When you start doing something, you try to use or implement a finite difference approximation for derivative pricing, you run into complications, and then these issues start making sense, like the coordinate transformation or non-uniform spacing, how you account for it, or the dimension reduction issue where real-time computation requires you to reduce the computational burden at any point of time. So dimension reduction is a slightly nuanced issue, because first of all, you have to map your rectangular grid to a tree, and then use the logic that you use in the tree to reduce your computational burden and translate back into the rectangular grid, where you are going to again reduce your computation burden by taking a subset of the grid, relevant subset. Is it clear?
Yes, sir.
So once again, I will reiterate that some of these problems only start making sense when you are writing your own programs. You are writing a program to solve an exercise, actual exercise. Then they start making sense. So the sooner you start doing the exercises, the better, because why these questions are important, that may not be apparent right now, but it will become clear once you start doing the exercises. Okay, so these were the additional issues in the computation about boundary conditions, about uniform, non-uniform grids, and also reducing computational burden. Now let us go back to a few more examples of more complicated derivative contracts. So in particular, we want to focus on path-dependent options, because so far we only talked about the Black-Scholes PDE, which is analytically very nice. But if I go back to say Bermuda options or barrier option, path-dependent, then my computational burden immediately goes up. So we need to understand how they can be handled. So now our topic of discussion is pricing path-dependent options in a diffusion framework. And we will basically cover Bermudan options and barrier options, because these are our favorite examples. We have used them before also. And if you understand these issues, then other contracts can also be handled. These are good canonical examples. So first we will start with the derivative and then talk about the boundary conditions, the critical points, etc., and then bring them together to the solution. Okay, so let's start with the Bermudan option. Bermudan option, we will all know that it's an option where you are given the choice of exercise at a predetermined set of dates. So I have this set tau e, which is the dates T1 to TL, and you are given a call option. No, it's a put option actually. So this example is a put option. The only difference is, in an usual European put option, you can only exercise at the end, but in a Bermudan option, you have the choice of exercising at all these points, where typically the last point would be the expiry date. So that is our option. To price Bermudan option, we will assume that we have a grid on which exercise dates, the set tau e, coincide with the grid. So what we are going to do is, whatever grid I may have, I need to modify that grid so that all these T points on the horizontal axis are covered. So this is an illustration. So this is the original grid rectangle that we showed in figure 3.1 in the earlier chapter, chapter 3. Now, in that original grid points, now we are going to add a few more verticals. These dashed lines, as required, these dashed lines we will add on to accommodate all the points in the set tau. So these are the points which are, suppose these are the points which are not covered in the original grid. So we want to add them. And of course, if we add points and we want to still keep the grid uniform, then we may have to add some additional points. And that's where the non-uniform grid point strategies come into play. That in order to accommodate exercise times, if I have to accommodate a very fine grid, that will increase my computational burden. So we can talk about the non-uniform grid points. But anyway, that issue we will tackle later. For now, let us simply say that we have modified our grid as required so that the set tau e is covered by the grid. So this is our new grid. Now, suppose the last exercise date in calendar time which is of course the first time point in terms of our tau axis, because tau axis is reversed. So the last exercise date becomes the first one on the tau line. That coincides with, say, tau k. So suppose tau k on the grid, the kth time step is the last exercise date, which is the first on the tau line. So then, up to that time step, there is no difference between a Bermuda and an European option. Right? Because after the last exercise possibility and till expiry, till maturity, there are no further opportunities. So it behaves like an European option. All right.
Yes, sir.
So it will behave like a European option since there is no exercise opportunity. And of course, then their prices must coincide. So when we have iterated from 0 to tau k up to tau k, we have basically a valid European option. And then we will have European option prices, Vk, for every asset price. So when I reach tau k, I have Vk for every asset price. Now we reach tau k. Tau k is where I have the decision whether to exercise or not. Now at each asset price level on the vertical on our grid at tau k, we should apply the optimal exercise decision. Now recall, this is the XM star that we talked about this morning, where I am exactly indifferent between continuing and exercising. So basically, what we check is whether my price level at tau k is above or below that optimal exercise boundary, XM star. So I can either choose not to exercise if the option value is better than current exercising. Otherwise, I will exercise and take that value. And that value is exactly known at that point. So at every exercise opportunity, what we do is we correct the option price. So what happens is at tau k, there is a change in Vk, because it is not only the value of an European option, but it is also a possible exercise at that point of time. So the value is actually going to be more than the European option value, because it's the maximum of these two. Okay, is this clear? This is the same kind of logic that we used in evaluating the American option using a binomial tree. At each step, we evaluated exercise and continuation. So the value at that point is actually maximum of the two. It's the same kind of situation here. So at tau k, that's what we do at step k. So this is the corresponding algorithm. So this is called pseudocode by Hitsa. This is probably a standard terminology, but this is the algorithm for me. So what I'm doing is, for each time step, k equal to 1 to capital M, some of these time steps will also be possible exercise dates, because this set must contain tau e. This set must contain tau e. So for each time step, I do the implicit valuation for Vk plus 1 using the implicit scheme, let's say. So I'm using the implicit scheme and I'm looking at a call option. That's the example. So I evaluate. Now for each asset value, now I equal to 1 to capital N means I am moving across the vertical. For each asset value, I evaluate whether the Vk plus 1 entity is less or more than the current, the exercise at that value. So this is the exercise value and this is the option value. So I compare these two. So what is it saying? I will revise my value upwards if it is less than the exercise value. So if it is less than the exercise value, then I just revise the value upward, because it must be maximum of the two. It must be maximum of the two. So if it is more, I do nothing, because then continuation is anyway optimal. But if exercise is optimal, then the value at that point has to be revised upward, and it will revise upward to the exercise value at that point, so that the contract still keeps me indifferent at that point. Is this logic clear? So recall binomial tree American option calculations, where what we did there was, at each time point we compared between immediate exercise and continuation, and we took the one which is better for us. So the value at that point would be the maximum of these two things. So we are using the same logic here at multiple time points. At each possible exercise opportunity, I am looking at the option value only, which is the V vector. Because it's also an exercise point, then there is an alternative. For a call option, the alternative is given by Si minus K plus. Whichever is better, then that should be the value of the contract, the modified value of the contract at that point, tau k. So the V vector, once I come out of this loop, this V vector will become a pointwise maximum of these two vectors, the original V vector and the exercise vector. Is this clear now?
Yes, sir.
So I will stop here. I will not venture into other things today. But this is a very important piece of algorithm or pseudocode, whichever you call it. And this you need to understand very clearly. If this is clear, then all the backward induction kind of algorithms that we are using earlier and now and later, they will be much clearer to you. That everywhere where I have a choice, I evaluate both the choices. I do two things. One is I revise my value function upwards if the exercise choice is better. And also I find a critical value of the stock. When I'm evaluating this inner loop, I loop, I will usually find a particular stock price above which I will do one thing and below which I will do the other thing. So basically, if the stock price is too high, then I will exercise my call option immediately. If the stock price is too low, I will continue. And there should be a point, a critical point, where I will be just indifferent between these two decisions. So my vertical axis will be typically sliced into two parts. So think about this a little bit more. We will come back to this on Friday, when we will continue discussing some other option contracts, some other path-dependent option contracts. For today, I think setting this scenario is good enough, that we have Bermudan options with TAUE exercise set. We accommodate them in the grid, and then we make the adjustments in the value function at all the exercise time steps. Okay, so if there are any immediate questions, I will take them, or we meet day after tomorrow.